So welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project, funded by the Exascale Computing Project. The series is a collaboration involving the U.S. Department of Energy computing facilities, the Argonne, Oak Ridge, and Lawrence Berkeley labs. I'm Mosny Marcus from Lawrence Berkeley, Ashley Parker from Oak Ridge, and I will be the hosts for today's webinar. Testing strategies when learning programming models and using high-performance libraries. The webinar will be presented by Balint Joe from the Jefferson Lab in Virginia. Balint got his PhD in theoretical physics in 2000 at the University of Edinburgh in Scotland, and since then has been working with numerical lattice QCD calculations. He has worked with the QUDA and the Chroma software packages, and he has been a staff computer scientist at Jefferson Lab since 2005, where his work includes maintaining and developing Chroma and porting and optimizing it for new architectures. He's been working closely with NVIDIA and the QUDA library, and more recently with Intel on code for Xeon and Xeon Phi. And basically, Balint runs Lattice QCD calculations on all computers he can put his hands on, and he's going to tell us what he has learned about testing and strategies. Balint, please.
Hi, everyone. My name is Balint, and I'm happy to hold this webinar for you. If we can, I will start the screen sharing and share my screen. And hopefully, we should have the slide deck up on the screen. So it's a pleasure to be here. And
it's not there yet, I think.
Is it there now?
No.
Oh, good heavens.
Yeah.
I am sharing, but maybe I'm sharing the wrong screen. Let me try again. This worked a moment ago, right?
Now, yes.
Okay.
Good to go.
Good to go. So it's a pleasure to have everyone along, and thank you so much for joining me today and to listen to me talk about testing. And the basic upshot I wanted to do today is to basically teach you a little bit about testing as a way to understand your programming models or to check your integration with some high-performance libraries. And to just set the scene a little bit, let me mention a bit about my own code that Osni has already mentioned in his very kind introduction. So basically, I work with an application called Chroma, which is a Lattice QCD code, and it's used in nuclear and high-energy physics calculations. And when this code was developed, the collaboration I work in, the US QCD collaboration, developed a layered approach to software through various iterations of the SYCL program. And I have a rough picture of this on the right-hand side. On the bottom layer, we have a small wrapper library, which wraps, in our case, MPI. But on some computers, we wrote our own version where MPI wasn't available. And then on top of this is, in the red box, you can see the QUDA library, which provides kind of a data parallel API for us to write our code over. And then we have some performance libraries. As Osni has already mentioned, there's the QUDA library, and I've been working recently also on Xeon Phi to write the QPhiX and MG Proto libraries. And these usually provide high-performance solvers for us. And the top box here is the Chroma application. And what I tried to do in this picture, I basically did a very quick run of slok count over each package. And that's just to give you an idea of the size of each package. So as you can see, QUDA and QPhiX, they're relatively small libraries, but that's where nearly all of our performance critical work goes. And QUDA itself is a relatively small library. It just provides a foundation layer, and the majority of the code is in Chroma. These layers encapsulate different responsibilities, but if you were thinking about moving this code to a new machine, you'd probably start off with QUDA++ and one of the performance libraries, and you'd get the majority of Chroma ready to go as a result. So let me say a few words about how this is tested. I was very glad because I think thanks to work from our friends in the UK, Craig McNeil, and also folks here in the US, my colleagues, Chroma was one of the very first QCD codes that had systematic nightly regression testing. Now, we've had some changes, and I'm not entirely sure that the testing setup is still there. But one thing about it is that it only tested things for us on CPUs. The QUDA library was tested independently by the NVIDIA developers. Had continuous integration on Travis. But at some point, it started to run afoul of build time limits because it took a long time to build due to auto-generated code. And last time I looked on Travis, the setup has decayed since the graduate student who set it up has moved on to other things. MG-Proto has lots of unit tests. As I developed it, I tried to do it in a test-driven way, but it doesn't have a CI step at this point in time. And QDP++ and QMP were essentially tested through the regression threads of Chroma. So I'm perhaps maybe not the best expert in the world to talk about systematic testing, but any testing is better than none. And CI for this stack is still an aspiration for us. There are other Lattice QCD out there now which have full continuous integration, such as the grid code, and I have links to that here in the text. But before I go on, I will also say that almost all my work is with C++, and I will focus on C++ unit testing. However, if you're a Fortran user, you might consider using pfunit, about which there was a seminar as part of the IDEAS project, and I have a link to pfunit in this document right there. Moving on to slide 4. So how do I do the tests? What kind of tests can we do? So QUDA is a third-party library that supplies the solvers we use. The lead developer is my friend and colleague, Kay Clark from NVIDIA, and it's maintained by a fairly large community. 3 or 4 developers at NVIDIA, I think, work on it, and it's also being developed by the Lattice QCD community worldwide. And the way Chroma uses QUDA, as you will see later on in this talk, is it wraps the calls to the QUDA library. And so we can make some nice test integration where we can create a wrapped Chroma objects. I can then call them, and I can compare the output with some less, perhaps less performant reference implementation. The testing is also useful, for example, when we try to add new features to QUDA. Recently, I have been doing this with Wei Sun, who is a postdoc here at Jefferson Lab. We developed a feature in Chroma using the less optimized but simpler QDP++. Once we were happy that it was doing the right thing, then we added the feature into QUDA, and then we tested the integration using our Chroma reference code. And so also nowadays, when I write new code, I always try to immediately add tests. I won't say it's 100% test-driven, but one example for when I was trying to write a solver, it has a sub-process called an Arnoldi process. I could always add in little tests to check the resulting vectors for orthonormality and things and like that. But one important thing to bear in mind is if you're testing against a reference, you are only guaranteeing bug compatibility with the reference in principle. So you should be happy that your reference is doing what you want first before you use it as a reference. So that's how much I wanted to say kind of as an introduction. And now I will go on to slide 5, where I say, of course, now things are about to change. We have the new exascale systems and pre-exascale systems coming online. The first of these coming along will be Parameterised at NERSC, which is a pre-exascale system powered by NVIDIA GPUs and AMD CPUs. Aurora is coming to Oregon Leadership Facility, and it's powered by Intel Xe technology and Xeon CPUs. While Frontier at OLCF, and as it's recently been announced, El Capitan at Lawrence Livermore, is going to be an exascale system powered by AMD exascale systems powered by AMD GPUs and CPUs. And some new programming models are coming. So when I put my QCD hat on, I said, okay, Parameter, it's NVIDIA. Phew, that's great. Existing QUDA code and the QUDA library were just fine. But then when I found out about Aurora, I went, uh-oh, there's no QUDA. And in fact, the preferred performance model is DPC++, which is based on SYCL. And when I found out about Frontier, I said, oh no, no QUDA. So the preferred programming model is actually HIP. Or if you like to go for performance portability, you can try and use Kokkos, for example, with its developing HIP and data parallel backends. And so I have a link here to a previous IDEAS talk, I think the last one in the series, before this one, on Kokkos. So one question that comes to mind is, how do I learn these new models? How can I make informed decisions? And my answer is, if you can, develop a MiniApp, a small MiniApp, and explore the performance, the programming model features by writing tests. And so again, I just highlight the fact that I'm going to talk about C++-based unit testing for the next few slides, but Fortran users can look at PF unit. Before I go on to how to do the nuts and bolts of unit tests, I'm going to pause here and ask if there are any questions at this stage.
No questions yet, Balint. Please go on.
Very good. So let me talk to you about unit test basics. For those of you who have never written unit tests, what you typically try and do is you want to form an expectation of what you want your code to do, and you should sort of exercise the expectation and then check that it is fulfilled. So I have on the right-hand side here, and of course, the way to check your expectation is what's done. The standard is to use assertions. So you can assert things are true, or you can assert things are equal. And I have on the right-hand side here a basic test from the Google Test API, which is what I will use throughout the talk. So let me highlight the parts. On the top, in the slightly darker pink box, I'm trying to exercise behavior. I'm looking at a SIMD complex number type, and I assume it has 4 lanes in this case, and I'm trying to set each lane to a particular complex number. And once this is done, I can verify the behavior basically by inspecting the lanes, which exercises the operator parentheses as well. And at the end, I make an assertion that everything is all right. Assert double equals is different from assert equals in the sense that it allows numbers to be equal within a small double precision epsilon. So that's the basic of the test. And now I will say a few words about data parallel C++ and SYCL, so we can see how we can exercise its features using tests. So here's my kind of one-slide summary of data parallel C++. I have an image on the left, on the right, sorry. And so typically today, some kind of compute node will have some number of devices. Some will be CPUs, some might be GPUs. I have a CPU on the left and a GPU on the right at the bottom. And you basically submit work to these devices using a command queue. And that's indicated by the funnels. And the work you submit to them is called the command group, which is why you will see the letter CGH in CGH single task, CGH parallel 4, because CGH refers to command group handler. And then interaction with the memory is through an abstraction called a buffer in SYCL. And when you define buffers, they work, you basically can only access data in them through these things called accessors, which you get by this getAccess function. And basically, you get access to the buffer, then you can access the data in it, and depending on whether you access it from the CPU or the GPU, the runtime will move the data there for you. So that's kind of the model. So key concepts are things like command groups, command queues, accessors, and you have these parallel constructs called parallel for or a single task. And I also think that I may have made a slight typo where I get the accessors. The CGH is actually the argument of the getAccess function, and I think instead of CGH, I should have the buffer name. But modulo that, I will stop for a moment and ask if there are any questions about this basic overview of data parallel C++.
No questions.
Okay, so now how do we run tests in such a situation? So first of all, as I walk you through how we can run various tests and exercise various features, we will also learn the various ways of writing tests and test fixtures. So when I was learning SYCL, we needed access to these queues, devices, buffers, and so on. And one thing you can do if you want to have a group of tests together is you can set up something called a test fixture. And in this test fixture, you can collect various things you're going to use by all your tests. So in this case, I have a queue, which I'm going to use in all my tests. I have a buffer that I'm going to use in all my tests. Also, I have the size of the buffer as some constants. In order to make this test fixture, I have to derive my fixture class from this test from this class called testing.test, which is provided by Google Test API. And then you can see in the constructor here, the queue is initialized on a CPU selector. So all these tests will actually run on a CPU device. Incidentally, you should know that in SYCL Data Parallel API, the CPU is a device, but it is also the host, but they don't talk to each other necessarily directly. So if you want to run something on the device versus the host, you still have to make a distinction. So in this instance, I have a function called setup, which is used to basically set up all these initial things. And this setup function will be called before every test you write. And what you can see, I use this setup to basically fill my buffer with some predefined values. There's also a function called tear down. So if you allocate memory, you can override the tear down function, and it can free the memory for you so you don't have memory leaks. In my case, I don't have anything that doesn't get automatically deallocated, so I don't have a tear down function. So this class definition here will basically generate a test fixture, and I can use its name to define tests now. So I have on this slide two tests. If you use test fixture, instead of defining your tests with the test macro, you use this test_f macro, and you put the fixture name. That's the name of the class you just defined. So the first test I have on the left-hand side at the bottom just checks that the buffer is filled with the appropriate values that I intended to fill it with. You can see in the first line, I get access using a host accessor to the buffer, and then I just go through it and check things. On the right-hand side, I now have a test that runs on the device, and this will now test a functionality called context load. And here's the thing, I can't really run the assertions on the device because the Google test doesn't work on the device for me. So the way I have to do things is I have to do something on the device, write the results into a buffer, and then on the host, check this buffer. And that's what this test does. So as you can see again, I define it with test_f, and I give the previous fixture name. The test actually submits to a queue. And in order for the queue to be completed, I either need to put a wait statement, a queue wait statement, or I need to have a scope around the queue submission. So that's why there's an extra set of braces that are outside the pink. And here I'm just using a single task feature of SYCL. I'm only wanting to do a single number. I want to move it from, I want to copy it from position 0 to position 1 in my array. And then once this is completed, I can use the host accessor, and I can read using the load lane function, both from position 0 and from position 1. And then I can check that those things are indeed the same. So this way, you have just checked that you've done something on the device, whatever the device is, and you have used host accessor again, and you submit it to the queue, and more importantly, you've added to the test fixture. Let me stop and ask if this is all okay. Any questions?
This is all okay.
Okay. So the next thing that can happen is you might have a situation where you want to run a test multiple times using different compile time constants. So one example, in my case, again, going back to SIMD type, is I may have different SIMD lengths. In SYCL, there's this vector type, and I've defined my SIMD complex number. And I want to check that it works for not just a SIMD length of 1 or 4, but for a variety of SIMD lengths. So what I can do in this case is I can template my test. And there's an interesting issue here that I want to use, if I want to template my tests, obviously I can just template it like I do in the pink bit. You still derive the template from testing test, but now you have to somehow define what values of the template you're going to instantiate your code for. And that's what this green box shows. You can have a testing type, which is a list, a type list, and inside it are all the template parameters. And here I'm just basically trying to give the vector length as a compile time constant because I use it in a template. So I can't give it as a runtime parameter. It has to be compile time. And so by going through by defining this testing types, test types type list, I can use the standard integral constant type to hold the actual integer types I want to use in my templates. So what this green box says is that there will be something like 4 instances of my laneops tester template, and each one will have a different integral constant given to it as a template parameter. And then in the green box, you can see the first thing I do is to use the type param : value, which gets that integer constant out of the standard integral constant type. And the only other difference is that I need to have this yellow box, which says that please instantiate the laneops tester class for all the types that are in the type list test types. And apart from that, everything is the same as before, except now I can access type param : value, and now I can test my code for all the SIMD lengths I'm interested in. And of course, you can use this for other types, and you don't have to use them necessarily for integers. You can use them for actual template types where you need a type and so forth. And let me go on finally to runtime parameterized tests. So in this case, the example I have is when I was working and I was writing an FGM-ResDR solver. And what I wanted to check is that this solver works for a variety of different target residua that I wanted to try. And so in this case, the target residuum would have been a runtime test, a runtime parameter. So how can I do this? In this case, first I derive my test from testing.test as usual, but I also want to derive it from this with param interface class or template. And so this is a bit, in C++, I try to avoid multiple inheritance, but this is how this template library was designed. This testing library was designed. So in the green, once I'm done with the green box, I now have a class that can have a parameter, which is a floating point type. And the tests that I use are now defined with the test P macro. I guess P stands for parameter. And just like I could get the test param before in the templated case, here I can access the testing parameter using this getParam function. And finally, I need to create instances of the test case, just like I did for the templated case. And that's done in this orange box here, where I can instantiate this, test case with something like 2 separate values that I will use for the target residuum. Okay. So then one last thing before I stop for a moment. Sometimes when you work with libraries or you're running MPI or you're working with Kokkos or something like that, you may need to initialize this environment somehow. You might need to call MPI init or MPI finalize, or in my case, it's typically Chroma initialize or Kokkos initialize or something like that. That can be done by an object called a test environment. So a test environment can have a constructor that can, you call it directly by creating an instance of this test environment. So you're free to choose what parameters it has. Google Tests doesn't necessarily circumscribe it. So in this case, I have an environment that you can see on the right-hand side, which is called Chroma environment. And this can take the argument count and the argument values as usual. And it also has setup functions and tear down functions where you can initialize or finalize Chroma in this case. And the trick is that the way Google Test works is first you have to initialize it, and then you have to call this run all tests macro. And if you just use the Google Test main supplied by Google Test, this is what it does. And you have to, if you want to use a test environment, you have to create it and add it to the environment before you do this run all tests call. And a simple way to do that is to just rewrite your own main function. And you can see it's just an extra line in there in between init Google tests and run all tests. So you can, for example, see I add the global test environment and I create a new Chroma environment and I'm done. Another way to do it, I guess, is you could do a static creation and then you can use the existing gtest main, but then you're kind of a little bit at the mercy of the order in which compiler instantiates stuff. So it's safer to do it with your own main function. So before I go on to some example tests and my canonical test setup and showing you how to set all this stuff in CMake, I will pause again to ask if there are any questions at this time.
Yeah, there is one here that I think the participant is just finishing typing. Any good test programs that work directly on the GPU or accelerator?
So I don't know about those. I don't have a good answer for that. Any other questions?
No, that's all for now. Please continue.
But you can always try and test by making the GPU do something and then bringing that something back to the host for testing. And then you can just not do it in production if you don't want to, if it's too much of a performance issue.
Okay. So there is more from that question. Does SYCL take care of that? In other words, put your tests in the DPC++?
So in DPC++, I have not been able to run my assertions on the device.
Okay.
So I always run my assertions on the host, and that might be a feature of Google Test, perhaps. Other test frameworks might be better at this, but I have not been able to do that with Google Tests. I always ended up writing to a buffer and then looking at that with a host accessor, kind of like in this example, right? So in the example here on page 11, you can see that the single task operates on the buffer, and then after the single task is finished, I access in the yellow box from the host now what the single task has written in there.
Okay, please go on.
Okay, so I typically, as I said, both because I developed with QDP++, and I usually nowadays, when I want to start some little project, I will have some kind of test setup like I have on this side here. And this is something that I built reading this book called An Introduction to Modern CMake. And I like using CMake for these kind of things because it really makes testing quite easy. And I will show, and also the integration with Google Test is quite well developed, as I will show in the next few slides. And you can see the kind of generic project directory here. Typically, I have a project, and I also have QDP++, and that's to provide the reference. And then in my project, I will have this external Google Test directory. So I usually add Google Test as a submodule, and then you can just check out the project recursively. You'll get Google Test automatically. And then I have a test directory in which I put my reference code and test environment and things like that. So I have a little GitHub repository, which I have not made public primarily due to the fact that I use things from An Introduction to Modern CMake, and I haven't figured out the licensing aspects. But it looks something like this. I have it on screen. I call it a CMake shell. And you can look in the external directory. There is Google Test for you, and I have a variety of sort of boilerplate introductions. So how to access CMake variables and something to test, something simple. And then in the test directory, I have some test code that has some simple test. I have no assertion here, which means this test will always succeed. So it's just to make sure the mechanics work. So going back to the talk. Right. And of course, if you were working with Kokkos, you can also add Kokkos as a submodule in the external directory and so on. The env.sh shell script I just use primarily to set up my environment, load any modules, define any compiler flags, things like that. And then I have these two scripts for build QDP++ and build project, which will basically run CMake followed by make for the project as needed. Now, testing it's easy to do in CMake, quite irrespective of Google Tests actually. Basically, if you include ctest, then I would advise that any reference code or test environment or what have you, you can add into a library. I usually call this library test utils. So in this instance, you can see I've got some QDP++ files and some d/code test env_cpp, which sets up the sort of Chroma environment kind of things. And then once you've made this library, you can link everything you're going to use to this library. For example, Kokkos or gtest, UDP. And now whenever you link against test utils, you will transitively get the other dependencies. And the nice trick I saw in this introduction to modern CMake is to make a macro that not only creates the executable with the add executable statement and links the libraries, including the transitive dependencies, but at the same time, you can also add a test with the same name as the executable, and the command just executes basically the executable. And you can make this command more elaborate, by the way. You can have commands on MPI. You can do all sorts of stuff. And then finally, now I have two tests in this instance. One is to test Kokkos features, and one is to test performance. And just one line for each of them will add those tests to Google Test. And you can run the test with make test, or by running a program called ctest directly. Or you can actually run the individual executables directly by hand, and they get a few extra options from Google Test. And the most useful ones I found were --gtest list tests, which lists the available tests you have, and --gtest filter equals, and then you can give some kind of filtering pattern, and then you can run only the tests that you're interested in. And that can be useful if you're if you have a lot of tests and you're working on debugging just one and making it pass, and you don't want to run all the other tests because you want to just pay attention to the output, then gtest filter is a helpful flag. So I have here a mini application, and this is a screen full of code. So again, let me just highlight it basically. On the right-hand side is our test. So this has several parts to it. The top part is I first just initialize my system and generate some synthetic data. This uses my QDP++ reference stuff. Then the blue part underneath, I will now generate some of the data types used by the thing I'm testing, and I import the data. So you can see lines here like import gauge field. If you're not an expert at QCD or you don't know anything about QCD, it doesn't matter. The purpose is just to see what each bit does. And once I've generated my data types in my tests and imported the data from my reference, then I can carry out both the reference computation, which is the two lines in yellow, and then I can test the optimized representation, that's the three lines in orange, and at the end of it, I just export the result out. And then finally, I can check correctness to some required level of precision and have an assertion. On the left-hand side here, I have my reference code in this case. And as you can see, because it's written in QDP++, this is very, very simple code. whereas the more optimized code is definitely more complicated. And I'm not even going to show it to you here on the screen. So this is what I meant by saying have a MiniApp where you have something maybe not necessarily the most performant, but good reference to check against. And then you can go and you can write lots of useful tests. And then, of course, you can also write a test which just checks the performance of your optimized case. So now, if I run make test or if I run ctest, I'll get the output on the top left. And this is usually quite condensed. So all it just says is I've got through this test and this test has passed. Or I can run the test Kokkos executable directly. Then I can see the standard output. I can see that Kokkos is initialized. I can see that QDP++ is initialized. I can see how big my lattice and so on is. But at the end of it, it just says that I passed the test. And if you have coloring turned on in your terminal, passed is almost always in green, and failed is always in red. So that gives you a nice visual guide. Okay, so that's what I wanted to say about writing a MiniApp and testing things. In this case, this was a Kokkos test. Before I go, now the next part I will talk about is about integration with a library. But again, I can stop and ask if there have been any questions at this point.
All clear, please go ahead.
Okay, so another thing that can happen, as I mentioned earlier, is that you're working with a library. In this case, I work with the QUDA library. And the way this works is that I wrap this up in Chroma. So the features that QUDA provides look a lot like features Chroma provides. And then I use a factory function, which basically reads some XML parameters from a file usually, and it generates some objects. And then I call methods on these objects to do my work. So the objects in question might be a linear solver or a linear operator or something like that. So how can I test this? Well, the first part is dealing with the XML. So I don't want to have separate files necessarily if I can get around it. What I can do is I can basically keep the XML as a string in a header file. And I have a snippet of that at the top. And this is some solver definition, and it's quite long and complex. So I just cut it short here. Then in my tests, I can use the reference code to basically deal with this XML. I turn it into a string stream, and then I can read from that. And then finally, I call this factory function called s_sim, which stands for symmetric action. And it has a method on it called invaluable, which gives me back a solver. Please excuse me. The one issue, though, is this, factory functions return to us instances of a base class. So if I have a lot of different kind of solvers, I have some base class that makes them all look the same. And so if I just look at linear solver on its own, I might not be able to get QUDA specific internals, which I may need to drive pieces of it. And so I've written this extra function underneath called getSolver, and this will try and cast back to the original class, which is not the base class. In this case, it's called linopsyssolver QUDA Clover. And then when I have that class, I can try and look inside it to see what's going on in terms of its public internals. So armed with all of this, I can now write the test. So the first thing I do is I call this getSolver function, which will give me the upcasted object. And then I can get its inverter parameters, which controls the behavior. And the way QUDA happens to work is once I set up a solver like this, I can call other QUDA functions with its inverter parameters, just like applying a matrix, for example. So the test I want to do here is I want to make sure that the linear operator I have in a particular linear operator I have in Chroma is the same as the one in QUDA, because that's kind of a first step. If the linear operators are different, the solvers will do different things. So I want to just make sure that QUDA and Chroma agree on what the linear operator is in this instance. And the way I do it is similar to before. I make some synthetic data. So I fill some source vector with Gaussian noise in this case. That's done in the kind of orange, pastel orange slide box. And then I apply the Chroma's own operator to it. And I get some kind of result vector. Now, QUDA knows from its inverter parameters what the layout of my data is. It knows about QDP++'s internal layout. So all I need to pass to the QUDA library call are pointers to the Chroma data, the start of the Chroma data, and this inverter parameter. And then this mat_QUDA is QUDA's function call for applying a linear operator. It will basically read in the data from the source pointer, shove it down to the device, apply the QUDA operation, and return the result to the host. And then I can check the result. So again, this is a situation. It's very it's very QCD specific, but the point is I can use this kind of test to basically test the library integration. And this is very handy because if QUDA changes, I can always use this program now to check that my integration is good. Or if QUDA users report errors, I can liaise with Kate Clark at NVIDIA, who's the lead developer of QUDA, or any of the NVIDIA colleagues who maintain QUDA, and just try and see whether my test breaks as well. And this is handy for finding kind of configuration bugs. We had an issue once where a flag changed its meaning in the input file, and in my test you wouldn't see it because my test set that flag, but a user who forgot to change their input file or didn't know they had to change their input file got bitten by it. But we could track it down with a test like this. So what else could be testing? Well, one can test performance. These tests typically report their runtimes, or you can just measure the runtimes and make sure that if the test is running too long, then you can automatically fail it. There's a special assertion called fail, which will just cause the test to fail. Or if you don't happen to have any reference code, you can imagine checking symmetries or other invariants. So for example, if you're doing Lattice QCD, you could check gauge invariance of things, gauge covariance of things, you could test conversation laws, and so on. And this brings me ultimately to my summary. So let me just sum up what I have basically said. I think that testing is a good practice. It can range from small unit tests all the way up to full continuous integration. But in this particular talk, I really wanted to focus on the fact that, in my opinion, I think it's a good way to learn about programming models, especially in combination with MiniApps. So you could learn about things like SYCL buffer management, or you could learn about Kokkos views, all these parallel constructs, any SIMD issues, and the tests will essentially document these for you for later times. It is useful to have a reliable reference code, which in my case is QDP++, but you can always check other things. If you don't have any reference code, you can check scaling behavior, you can check performance, you can check conservation loss, symmetries, all those things. And for C++ programmers, there are now many testing frameworks out there. I did a quick search on Google. While I focused on the Google Test API, there are others out there. So ones I found were Catch, Boost Test, CPP Unit, and so on. And then if you're a client of a rapidly developing library like QUDA, which is developing quite rapidly and is developed by many users, it is very helpful to have integration tests so that you can check that what works today also works tomorrow. And if it doesn't, you can track down easily what was the cause what was the change that made things break. If you're a CMake user, adding tests is very easy. And I hope the examples here will help you write useful tests of your own. And I have a whole page here of summaries of references, including links to the IDEAS project, but also to the Google Test API, the book I mentioned, Introduction to Modern CMake. My MiniApps are freely available on the web. The QUDA library, Kokkos, SYCL, One API. Stack Overflow is always an excellent resource. And one other IDEAS talk that I saw that was maybe interesting in this point of view is one about continuous integration. And that's all I have to say today. And if you have any questions, I would be very happy to answer them for you. I just want to finish off by thanking my sponsors. Thank you.
Very nice, Balint. There's a question here for you. In my experience, the ALCF Argon admin can install anything you need. when you said that Aurora does not have QUDA, why can't the admin install QUDA?
Well, I think the issue is that QUDA is an NVIDIA-specific programming model for NVIDIA GPUs. And certainly, I think ALCF does have CUDA installed for NVIDIA GPUs, but CUDA will not drive the Intel Xe GPUs that are coming in the future system, unless a port of CUDA to Intel Xe hardware is made.
All right. So there is another question here. The participants is still typing. Just to give us a. Or give the participant, I think okay. So are you happy with Kokkos for performance supportability?
So far, based on my MiniApps, I am. And I now, I definitely have found that I can match certainly native CUDA on NVIDIA GPUs. By using a vector type of my own, I have managed also to match the speed of my own Q5X library on Xeon Phi. And now, of course, Kokkos is having its own SIMD types, which I haven't had a chance to check yet. And in terms of SYCL and HIP, those backends are maturing, and I have been trying out my MiniApp on prototype versions. So in that sense, yes, I'm happy. I published about it and everything. But what I have not done yet is to use it at a very large scale. And so I'm now working on taking those learnings from MiniApps and Kokkos and trying to apply it to more bigger scale codes.
So another question, Balit. Can you compare the performance of Kokkos and SYCL?
This is not very easy to do just because of the hardware features. So one thing that I have done, let me see. If you don't mind, I can try and pull up a paper about this or a presentation.
Yeah, please.
Open recent. Where did I have this presentation? Yes. So this is a talk I gave at the P3 HPC forum at Supercomputing. And here is my little MiniApp. And the thing to take care of is that here's a performance comparison graph, but I want to find the correct one, this one. So the only place where I can really successfully do this is, for example, on a GPU. I have SYCL, but I had to use an OpenCL runtime called Pockle. And there you can see that on the V100, Kokkos and SYCL, they give comparative performances to QUDA, but Pockle is an OpenCL runtime that's not sort of community supported, as it were. So one thing that's interesting is that Intel One API compiler, the LLVM compiler, now has a backend for QUDA, and that I have not yet tested. Another place where I tested both SYCL and Kokkos was on Skylake systems using the Intel runtime. And there, I think the vectorization still needs a bit of work in terms of my SYCL implementation. But again, Kokkos with the vector type did really very well. And I think the SYCL number that I have here is a little bit immature. On Intel Gen 9 GPUs, I do not really have a Kokkos comparison yet, but I'm working on that because the Kokkos data parallel C++ backend is not there yet. So I find the performances to be quite okay so far with Kokkos, and also with SYCL. And so then it's just a question of portability to other systems. And now data parallel C++ will have a nice CUDA backend thanks to the efforts of CodePlay. But I don't know, for example, if it will run on HIP. I might have to turn to a different SYCL implementation like HIP-SYCL. But this is a different talk altogether.
Sure. Well, you're going to have the opportunity to go through the questions and answers, and you could even, if you'd like, add this slide there when this. I don't see any other questions here. Ashley, would you give me the sharing here? Just, can you see my?
Yes.
All right, so my slide here.
Oh, I don't see your slide at the moment.
People are gonna see it now. Good.
It is.
Yes, so thank you very much, Bolint. I'd like to thank all participants again for joining us today, and please give us feedback. We'd like to improve this series. These slides and recording will be available at these two addresses sometime next week. And with that, I'd like also to announce the next webinar, April 15th, the tax day. Best practices for using proxy applications as benchmarks. And it's going to be presented by David Richards from Lawrence Livermore and Joe Glansky from HPE. And we are already accepting registrations there at that that address.